Hello everyone, myself Sarthak Nasid and my teammates Akash Yadav and Sandesh Banka will be discussing about the topic signal compression. Next slide. Signal transmission and storage cost money. The more information being dealt with, the more it costs. In spite of this, most digital signals are not stored in the most compact form. Rather, they are stored in whatever way makes them easiest to use, such as ASCII text from word processors, binary code that can be executed on a computer, individual samples from a data acquisition system. Typically, these easy-to-use encoding methods require data files about twice as large as actually needed to represent the information. Signal compression is the general term for the various algorithms and programs developed to address this problem. A compression program is used to convert data from an easy-to-use format to one optimized for compactness. Likewise, an uncompression program returns the information to its original form. Next slide. Signal compression strategies. So there are basically two methods. One is lossless and the other is lossy. A lossless technique means that the restored data file is identical to the original. You cannot afford to misplace even a single bit of this type of information. In comparison, data files that represent images and other acquired signals do not have to be kept in perfect condition for storage or transmission. All real-world measurements inherently contain a certain amount of noise. If the changes made to these signals resemble a small amount of additional noise, no harm is done. Compression techniques that allow this type of degradation are called lossy. This distinction is important because lossy techniques are much more effective at compression than lossless methods. The higher the compression ratio, the more noise added to the data. Next slide. So we will be discussing three types of encoding methods. The first being run length encoding. Data files frequently contain the same character repeated many times in a row. For example, text file uses multiple spaces to separate sentences, intent paragraphs, format tables, and charts, etc. Digital signals can also have runs of the same value, indicating that the signal is not changing. For instance, an image of the nighttime sky will contain long runs of the character or characters representing the black background. Likewise, music might have a long run of zeros between songs. So run length encoding is basically a simple method of compressing this type of file. Next slide. So this figure illustrates run length encoding for a data sequence having frequent runs of zeros. Each time a zero is encountered in the input data, we append two values to the output file. The first of this value is a zero, a flag that indicate the run length compression has begun. And the second value is the number of zeros in the run. So if the average run length is longer than 2, compression will take place. On the other hand, many single zeros in the data can make the encoded file larger than the original. Next slide. Many different run length schemes have been developed. For example, the input data can be treated as individual bytes or groups of bytes that represent something more elaborate, such as floating point numbers. Run length encoding can be used on only one of the characters, as with the zero above. Several of the characters or all of the characters. A good example of the generalized run length scheme is pack bits created for Macintosh user. Each byte from the input file is replaced by 9 bits in the compressed file. The added 9th bit is interpreted as the sign of the number. That is, each character read from the input file is between 0 to 255, while each character returned in the encoded file is between minus 255 to 255. To understand how this is used, consider the input file 1, 2, 3, 4, triple, 4 double twos, and 4, and the compressed file generated by the pack bits algorithm. So it generates 1, 2, 3, 4, 2, and 3, 4. So the compression program simply transfers each number from the input file to the compressed file, with the exception of the run 2222. This is represented in the compressed file by the numbers 2, minus 3. So the first number 2 indicates that what each character consists of, and the second number minus 3 indicates the number of characters in the run, found by taking the absolute value and adding 1. Next slide. And now my friend Akash will continue with the other methods.
Now, the encoding method that we are going to discuss now is Huffman encoding. So this method was named after David Huffman, who developed this procedure in 1950s. So as you can see in the histogram, it is a histogram of the byte values from a large ASCII file. And as you can see in the histogram, more than 96% of the file consists of only 31 characters, which include the lowercase English alphabets, the space, the comma, the period, and the carriage written. So we can use this observation to make an appropriate compression scheme for this file. So to start with this method, we'll assign each of these 31 common characters, which we have seen in the histogram, a 5-bit binary code. Like we can start from 000, assigning 000 to A, 001 to B, and so on for the next 31 characters. So this will allow us to this will allow us to compress the 96% of the file to reduce its file size by a factor of 5 divided by 8. And as we can see, we have used 5 bits for A. So there are a total of 32 combinations. So we'll be using the first 31 combinations for these characters, and the last combination, which will be 111, will be using it as a flag, which will indicate that the character that is being transmitted is not one of the 31 common characters which we have distinguished. So the next 8 bit in the file indicate what the character is. So according to the ASCII standard, this results in 4% of the characters in the input file requiring a total of 8 plus 5, which is 13 bits. So the idea is to assign frequently used characters fewer amount of bits and seldom used characters more bits. So Huffman coding is all about this. So Huffman coding takes this idea to the extreme. So characters that occur most often, such as the space and the period, will be assigned fewer bits, and the characters which are infrequent, which are very rarely seen, such as the exclamation mark, the hash sign, and so on, will be requiring more number of bits. So in mathematical terms, the optimal situation is reached when the number of bits used for each character is proportional to the logarithm of the character's probability of occurrence. So next slide. So a clever feature of Huffman encoding is how the variable length codes can be packed together. So imagine receiving a serial data stream of ones and zeros. So if each character is represented by 8 bits, we can directly separate one character from others. So basically we can divide the whole stream into 8-bit chunks and distinguish between the characters. Now consider a Huffman encoded data stream where each character can have a variable number of bits. As we have seen in the previous example, we assigned 5 bits for the most common and 13 bits for the infrequent ones. So we will be having variable number of bits for different characters. So this is a problem in Huffman coding, which we are going to see the solution. So how do you separate one character from the next in the Huffman stream? So the answer lies in the proper selection of the Huffman code that enables the correct separation. So now we'll be looking at an example. So as you can see in the table shows a simplified Huffman encoding scheme. So the characters A through G occur in the original data stream with the probabilities shown. So as we can see, A is the highest probable character, and the as we go down the table, the probability is decreasing. Since the character A is the most common, we'll be representing it with a single bit, and the next most common character is B, which will be using 2 bits. This continues to the least frequent character G being assigned 6 bits. So as you can see, the character with the highest probability is assigned a Huffman code with the least number of bits. So as shown in the table, the variable length codes are resorted into 8-bit groups. This the standard for which normal computers use. Next slide. So when this Huffman encoded stream is passed, when the uncompression occurs, all the 8-bit groups are placed end to end to form a long serial string of ones and zeros. Now, basically what we'll do to separate each character, we'll go on processing the encoded stream, and we'll look for the next stream of zeros and ones until we encounter a legitimate code for a character. So basically the decompression program looks at the stream of ones and zeros until a valid code is formed. So as we can see in the stream, we have encoded C, E, G, A, D, F, B, E, A, and you can see the Huffman encoded stream, which is 0010, 000, and so on. So this stream will be grouped into 8 bits. So you can see there are 4 bytes of total stream. And now we'll go on processing the stream. So first we'll encounter a 0. So 0 is an invalid Huffman code. Then we encounter a next 0. So we have 2 zeros, which is also a invalid Huffman code according to our example. Now we encounter a 1. So the Huffman code we have encountered is 001, which is also invalid. Now we again encounter a 0. So we have the code 0010, which is a valid Huffman code. So we know that the first character is C, and now we'll go on. Now we'll be looking for another character. So this is how we process the Huffman encoded stream, and we decompress it. A more sophisticated version of the Huffman approach is called arithmetic encoding. So in this scheme, sequence of characters are represented by individual codes, and this has the advantage of better data compression by 5 to 10%. To implement Huffman or arithmetic encoding, the compression and decompression algorithms must agree on the binary codes used to represent each character. So this can be handled in one of the two ways. The simplest is to use a predefined encoding table, which we saw, regardless of the information being compressed. A more complex scheme is to use encoding optimized for the particular data being used. So this requires that the encoding table be included in the compressed file for the use of uncompression program. So both methods are common. Next, we'll be discussing delta encoding, which will be discussed by my friend Sandesh.
So the term delta encoding refers to several techniques that store data as a difference between successive samples or characters rather than directly storing the samples themselves. The figure below shows an example of how this is done. The first value in the delta encoded file is the same as the first value in the original data. All the following values in the encoded file are equal to the difference between the corresponding value in the input file to the delta value and to the previous value of the input file. So next, so delta encoding can be used for data compression when the values of the original data are smooth. That is, there are typically only small change between the adjacent values. This is not the case for ASCII text and executable code. However, it is very common when the file represents a signal. For instance, figure A shows audio signal digitalized to 8 bits, where each sample between -127 and 127. And figure B shows the delta encoded version of the signal. The key feature is that the delta encoded signal has a lower amplitude than the original signal. In other words, the delta encoded has increased the probability that each sample's value will be near zero and decreased the probability that it will be far from zero. This uneven probability is just the thing that Huffman encoding needs to operate. If the original signal is not changing or is changing in a straight line, the delta encoding will result in a run of samples having the same value. This is the corresponding delta encoding is followed by Huffman or run length encoding is the most common strategy for compressing signals. The idea used in delta encoding can be expanded to more complicated techniques to like linear predictive coding or LPC. To understand LPC, imagine the first 99 samples of an input signals have been encoded, and then we are about to work on the sample number 100. So we ask ourselves, based on the first 99, what is the most likely value of sample? So in delta encoding, the answer is most likely to be the value of the 100 as same as the previous value, sample 99. The expected value is used as a reference to encode the sample 100. This is the difference between the sample and the expectation placed in the encoded file. The LPC expands on this by making a better guess at what the most probable value is. This is done by looking at the last several samples rather than just the last sample. The algorithm used by the LPC are very similar to recursive filters, making use of the own Z transformation and other intensively mathematical techniques. So this is the reference which we have used to make our PPT. And thank you. Hereby we conclude our presentation.